Unit 5, Day 1, Graphing Rational Functions. Today you are going to graph rational functions in vertex form. You are going to identify zeros, vertical, horizontal asymptotes, and holes. The function f of x equals 1 over x has a vertical asymptote at the line x is equal to 0, and a horizontal asymptote at the line y is equal to 0. A horizontal line is what y cannot be equal to, and it is denoted by this red dotted line. A vertical asymptote is what x cannot be equal to, and that is denoted on our picture by this green line. The function f of x equals 1 over x can be transformed according to the following rules. So when we look at f of x is equal to a over the quantity of x minus h plus k, if we look at our a, the absolute value of a is going to tell us if we have a vertical stretch or compression. If a is less than 0 or negative, it's going to reflect across the x-axis. If k is a negative number, it's going to be down. If k is a positive number, it's going to translate up. And when we look at our h, we want to think of the opposite. So if we have x plus h in our denominator, it's going to move to the left. And if we have x minus h or negative h, it's going to move to the right. When we use the graph, f of x is equal to 1 over x, the blue graph on each of these examples is the function f of x is equal to 1 over x. So we use that as a guide, and then we describe all of our transformations and then graph the function. So if we're looking at example A, this plus 2 on the bottom moves our graph left 2. So we can move our green asymptote to the left 2. Make sure you know left from right. So we put a dotted line, we move left 2. Our y is still equal to 0, so our red line's going to stay the same, and then our dots, or our graph, is just going to move 2 units to the left. Asymptotes are lines that our graph approaches but never crosses. When we look at example B, this 3 on the outside here tells us that our graph moves down 3. So we are still going to have a vertical asymptote where our green asymptote is as x equals 0, but our red or our y horizontal asymptote is going to move down to negative 3. So then our graph would move down 3 as well, but translate, but stay the exact same as our parent function. When we look at G, we notice that our 4 and our x are backwards. So whenever this happens, we want to make sure and factor out a negative. So 1 over 4 minus x is the exact same thing as saying negative 1 over x minus 4. So this negative on the outside here, which we associate with our A, is going to tell us that our graph flips. This negative 4 in the denominator is going to tell us that we move right 4, and this positive 5 is going to tell us up 5. So we're going to move our horizontal asymptote up 5. We're going to move right 4. So remember that denominator is opposite of what you think. And then when we flip over our x-axis, our graph is actually going to be in quadrant 2 and quadrant 4 instead of 1 and 3. So it flips locations. And you just describe these transformations and graph them. For a rational function of the form f of x is equal to a over x minus h plus k, the graph is what we call a hyperbola. There's a vertical asymptote at the line x is equal to h, which means the domain cannot equal that h value. So x cannot equal, the only x value that our graph would not touch is when x is equal to h. There's a horizontal asymptote at y is equal to k. The range for that means that the y value cannot be equal to k. So example 2 says identify the asymptote, the domain, and the range for each function. So when we're looking at our vertical asymptote, we want to look at our x, which is also our h. Remember, our h is down here on the bottom, and it's opposite, so we're going to say x is equal to negative 3. Our horizontal is our y, or our k. Outside stays the same, so we're going to have a horizontal asymptote at y equals negative 2. Our domain pairs with our vertical asymptote, so for every x such that x cannot be equal to negative 3, and our range pairs with our y values, so we say we want all the y values except for where y equals negative 2. When we look at example B, our vertical is the opposite, denominator is the opposite, x equals 3. Remember, our vertical asymptote corresponds to our domain, so for every x such that x is not equal to a positive 3. Horizontal, y equals negative 5. Our range corresponds with our y value, so every y value would be on our graph except where y is equal to negative 5. So these are the rules to determine zeros, vertical asymptotes, horizontal asymptotes, and holes in the graph. So I've simplified over here in purple the rules for zeros and vertical asymptotes. What this is saying is, in order to find your zeros, you set the numerator equal to 0 and solve. In order to find your vertical asymptotes, you set the denominator equal to and solve. So don't forget to solve to find those values. When we talk about horizontal asymptotes, we're looking at our function, and more specifically, we're looking at our p of x over our q of x. So we're looking at our denominator and we're looking at our numerator, and we're looking at those degrees. If the degree is bigger on the top, we are going to have no horizontal asymptotes. So you can see these little helpful hints in green. If the degree is bigger on the bottom, your horizontal asymptote is always going to be y equals 0. If your degrees are the same on the top and the bottom, you want to look at the leading coefficients of those terms. Holes in the graph are where the factors, so after you determine a horizontal asymptote, you're going to factor completely, and they are where the factors in the top and the bottom cancel out. So identify all the zeros, horizontal and vertical asymptotes, and holes in the graph of the function. So the first thing we want to look for is horizontal asymptotes. We want to look at our degrees of our leading term, and our degree on top is bigger, so we have no or none horizontal asymptotes. For our zero, after we look at our horizontal asymptotes, we want to factor. So we get x plus 3 over x minus 2. Put that over x plus 4. None of our factors cancel out, so we have no holes. For our zeros, we set our numerators equal to 0 and solve. So we have a 0 at x equals negative 3, x equals positive 2, and we have a vertical asymptote where we set our denominator equal to 0 at x equals negative 4. In the second example, our degree on the bottom is bigger, so we get y is equal to 0. We then factor. We have no factors that cancel, so there are no holes. Our numerator or our zeros would be at x is equal to 1. To find our vertical asymptotes, we set our denominator equal to 0, so we get x equals -2, x equals +2. When we look at example C, we see that our coefficients are the same. So we would do 6 over 3, which would simplify to 2. So our horizontal asymptote is y equals 2. When we factor our 6 out, we see that nothing cancels, so we have no wholes. Our numerator equal to 0, we get x is equal to +2. Our denominator equal to 0, we get x is equal to -4/3. Our last example, our degrees are the same, so our horizontal asymptote is those coefficients, which are 1, so we get y is equal to 1. When we factor this, we get x minus 3 times x minus 4 over x plus 3x minus 3. We have a factor that cancels at x minus 3, so we have a whole at x is equal to 3. We have zeros at x is equal to 3 and x is equal to 4. We have a vertical asymptote at x is equal to -3 and x is equal to 3.